All right, here we are for Honors Physics, Circular Motion and Universal Gravitation, Worksheet 1. Going to take a look at problem 3. It says, determine the centripetal force acting on a 75 kilogram person standing at the equator of the Earth due to the Earth's rotation on its axis. In other words, because the Earth is rotating, spinning around, if I got someone standing at the equator, that person is going in a circle. And so they would need to have centripetal force inward to make them turn, right? So what's that centripetal force acting on that person standing at the equator due to the Earth's rotation? What's the centripetal acceleration for them, that acceleration inward? What if the person moves to the North Pole or the South Pole? What effect would that have on that? So we're going to take a look at that, and notice I give you the value for the radius of the Earth at the equator. So here we go. So I'm going to do that on separate paper, give myself plenty of space. So we'll recall that when we do circular motion problems, it's often useful to draw two views. Let me draw the picture that was kind of shown there first. In the picture that was shown, here was the Earth and the equator, and here's the person standing at the equator. Okay, say this is the North Pole and here's the South Pole. Then the Earth is rotating kind of like this, right? Okay, so the sun rises in the east because we turn eastward. Anyway, so in this picture, the person is moving into the page away from me. In other words, I'm looking down the tangential axis in this picture. Okay, so if I drew my coordinate axes here, I'm looking along the tangential. The center of the circle is here. So this is the radial axis, is going to the left there. And then up and down here, this would be the third dimension. This would be the z-axis. And this is the radial. And I'm looking down the tangential. I could draw another picture if I'd like. I usually like to draw one that's looking down the z-axis, so it's look down this way. So I'd be looking down at the North Pole. Okay, I don't know why my Earth got smaller here, sorry. Looking down at the North Pole, there's the person at the equator. All right, and in this picture, again, they are heading towards the east. The velocity is this way. All right, so this is, and the Earth is rotating around like this, right? So this axis is the tangential axis along the direction of the velocity. The velocity is always tangent to the motion. That's the tangential axis. And then my center of the circle is here, right? We're going around like this. This is center. So the center of the circle is that way. So this is my radial axis. Okay, those are my two views. So now I'm going to go ahead and draw in my forces. Sure, why not? What forces are acting on this person? You'd say, well, there'd be a gravitational force. Which way does gravity go? Toward the center of the Earth. So there'd be a gravitational force like so. I would also see that force on this diagram, toward the center of the Earth, right? You'll notice that that's along the radial axis. We see the radial axis in both pictures. Now you go to contact forces. What's touching the person? Just the ground, right? Are they being pressed together? Yes, so there's a normal force going straight out of the surface, straight this way. We would see a normal force. Are they trying to slide along the surface of the Earth? No, we don't need like a friction force to hold someone steady. They're already moving this way. And so I don't have to keep pushing to keep them going that way. There's no force needed tangential. And there's nothing else touching the person, so we're done. Okay? We just have normal and gravitational, and that's it. So let me ask, do these forces balance out? You say, well, technically I'm going in a circle. I need to have a force and an acceleration toward the center of the circle to make me turn, don't I? Now, am I going to need a real big force toward the center? You say, how quickly am I turning? It takes an entire day for me to turn around once, right? Do you see what I'm saying? From facing that way to facing that way, that way, that way, that way. It takes a whole day. And so it's not going to be a huge acceleration we get out here. And so the difference in these forces, the total force, is going to be pretty small. All right, so it's not a huge difference. But you recognize that these forces cannot balance out, or else I wouldn't have an acceleration toward the center. So which is going to have to be bigger, mg or n? You say, well, I need to have an acceleration inward toward the center of the circle. So the normal force will be a little bit smaller than mg. So the normal force, how hard the floor is pushing up on you, actually doesn't quite balance out how hard the earth is pulling you down. Okay, because we need a force inward to help you turn. So there you go. There you go. Okay, so if we were to go ahead and do the calculation, we might set up Newton's second law. Sigma F is ma, and we're going to do it for that radial axis. It's the only axis we have forces in, so I guess we're going to analyze that one, huh? Right? We know the force in the radial axis is the force that makes you turn. That's the centripetal acceleration in that axis. So that's AC. And we have a special formula for AC. We know that AC is equal to V squared over R. All right. Now my forces, we always do forces in toward the center minus out from the center, right? In minus out, or centripetal minus centrifugal. In toward the center, that's mg. Away from the center, that's n. So that's what it's going to look like. Again, these forces will not balance. If they did, these would add up to 0. It wouldn't be accelerating. We wouldn't be moving, actually. V would go to 0, right? So they're not going to balance out. All right, so here's where it gets a little bit weird. Okay, so at this point, I'm just going to leave this alone for now. Let's focus on this side for now. All right, the mass of the person, we were told the mass of the person is 75 kilograms. So we have that value. All right, R, that's the radius of the circle. We know that. We were told the radius of the Earth at the equator, that radius would be 6.38 times 10 to the 6th meters. So we have that value. Now we just got to find the V. All right. Now they didn't tell us the speed at which the person is moving, but we know they're moving with the Earth's surface, right, as the Earth rotates around. And so we can do a little calculation for that speed. We can say that we know that speed is distance over time. And so the distance it takes for us to go all the way around divided by the time to go all the way around. Now the distance all the way around, that would be the circumference. That would be 2 pi r. And the time to go all the way around, that's with the repeated motion, that's called the period, which we abbreviate with a capital T. So to find that velocity, we're just going to take the distance to go around once divided by the time to go around once. Okay, we can do this calculation. We know the distance to go, the radius of the circle, we were told that, 6.38 times 10 to the 6th. Now I just need to find the time. Hey, what's the time it takes for the Earth to rotate around once? You call that a day, right? And so you say, well, I can't leave this in that unit, days. We don't want velocity in meters per day. We want meters per second. We've got to use the normal standard metric units for everything to work out right in the equation. So I have to convert. All right, so I'm going to do that. Do that here. So let's convert. Do you know how to change this period, 1 day, and turn it into seconds? Okay, this is a process we're going to use called dimensional analysis. This is something that hopefully you learned how to do in chem class. Okay, if not, it's actually not bad. But you recall that we're going to use conversion factors to change from one unit to another. Now, it's possible that some of you have memorized how many seconds there are in a day. I haven't. So I'm going to have to figure it out. So I'm going to do that by doing it step at a time. So I'll go from day to the next unit down that I know, and that's going to be hours. I want to change from days to hours, and then I'll go from hours to minutes, and then from minutes to seconds, and that's the unit we need, right? So I need to get rid of days. Now I got day on top, so to get rid of it, I'll put day on the bottom. I'm going to go to hours. Okay, now the time is 1 day. I can't change how long that time is. I just want to change the units it's measured in. What can I multiply a number by that won't change how big it is? Well, the thing you multiply by is to be something that's equal to 1, right? So conversion factors are always equal to 1. Now, when you have a fraction, as long as the top is equal to the bottom, that fraction is equal to 1. So that's the trick. In how many hours equal how many days? So the top will equal the bottom. Well, 1 day is 24 hours. So when I multiply by this, it's like I'm multiplying by 1. Something, the top and the bottom are equal to each other. I'm multiplying by 1. Okay, if I did this, the units, day would cancel. I'd be in hours. Well, let's keep going. Let's get rid of hours and go to minutes. How many minutes go with how many hours? You know that 60 minutes equals 1 hour. So the top equals the bottom. The hours units cancel. If I stop my calculation here, I'd be at minutes. We're going to go from minutes to seconds. Going to get rid of minutes, go to seconds. I know that in 1 minute, there are 60 seconds. Minutes and minutes will cancel. I'd be at seconds now. That's the unit I need. So I'm going to go ahead and do the math on this right now while I'm thinking about it. So we've got 24 times 60 times 60. That gives me 86,400 seconds in 1 day. And so that's the number of seconds that are the period for our calculation here. All right, that's the seconds in a day. All right. Okay, so we can calculate this. And you say, hey, wait a minute. In the problem, there's 2 things they asked for. They wanted to know the centripetal force, and they want to know the centripetal acceleration. Hey, centripetal acceleration, that's just v squared over r. We can calculate that now. So I'm going to do that off to the side here, which is something I don't normally do. Well, I'll do it here. V squared over r. So that v squared over r, that's just going to be, the velocity is 2 pi r over t. I want to square that and divide by the radius. I do still have, I'm just going to do this blue part, okay? Hey, if I square that, that would be 4 pi squared r squared over t squared. But wait, r squared, and I'm going to divide by an r, they'll just be 1r. Okay, so what that's going to equal, 4 pi squared, the radius, 6.38 times 10 to the 6th, divided by t squared, that'll be that 86,400 squared. So I'm going to get my centripetal acceleration out of that calculation. 4 times pi squared times 6.38 times 10 to the 6th. I'm going to divide that by the quantity 86,400 squared. When I do that, I get 0.0337, roughly. So 0.0337 meters per second squared. That's my centripetal acceleration. Done. All right. Okay, so that's that part. Now the other part was they asked for specifically now, determine the centripetal force acting on that person, da 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 da. Okay, so you say, well, what do they mean by centripetal force? Well, you're like, well, wait a minute. I remember that centripetal means toward the center. Aren't they just asking for the force that's toward the center for the value of mg? Well, no, that's not technically what they want. All right. This is kind of a physics slang sort of thing, okay? You know how the acceleration is toward the center, so we call it the centripetal acceleration? Sure. Well, if the acceleration is toward the center, then the total force in the radial has to be toward the center. In a problem, when they ask for the centripetal force, what they really mean is, what's the total force in that axis that we know has to be toward the center? Right, because that total has to be toward the center. They're really just asking for the total force in the radial axis. Yeah, I know. It's a little bit of physics slang, and don't sweat it. I'm never going to ask it that way again. So the point is, that total force, that's just equal to ma. So I just have to take this acceleration and multiply by the mass. right? That's really it, okay? So getting back to this, M times AC, right? I'm just going back to this line. The mass we know is 75 kilograms is the mass of the person. And the centripetal acceleration we just figured out was 0.0337. I actually saved that calculation in my calculator, so I'm just going to multiply that with other extra digits there, times 75. So the total force has to be 2.53 newtons. Okay, so that's what I'm getting here. That's the total force. That's the sum of the forces in the radial axis is 2.53 newtons. Okay, that's it. All right, that's really what they wanted. Now, if you want, we can go a little bit further. Okay, mg minus n. All right, so this is really, these are the answers they're like looking for in this problem. But let's go a little further. This is mg minus n, isn't it? How big is mg? Well, that's just going to be 75, the mass, times 9.8. Minus n is 2.53. So 75 times 9.8, okay, would be 735 newtons. The point I'm getting at here is the Earth yanks down on you with 735, but the ground will not push up with 735 because you need to accelerate inward to turn. It's going to be a little bit less. If I rearrange this, it'll be 735 minus 2.53. And so you say, gosh, you say that normal force would just be 732.5 newtons. So you realize that how hard you're shoved into the ground because the ground is turning also. It's like the ground, it's not like it is, the ground is accelerating in too, so that bit of dirt you're standing on can turn, right? You know what I mean? So it's like it's kind of accelerating in. It's almost like it's falling a little bit at this little tiny rate. And so you're also falling there. So it doesn't push up quite as hard because it's kind of falling with you a little bit. All right? Does that kind of make sense? And so this is the difference. And so what I'm saying is it's interesting to me that let's say you were standing on a bathroom scale there. How hard you shove on the scale, how hard the scale shoves back, that's what this little spring scale reads, is how hard the force is that it's pushing back on you with. It will be a little less than your actual weight. So the bathroom scale doesn't really tell how hard the Earth pulls on you. It's actually off by a teeny little bit here. Anyway, just interesting to note. The normal force does not, in fact, equal your gravitational force. Now, do we need to take this into account in our future calculations? And the answer is, nah, we're not going to worry about this. Okay. In fact, we will. We're not going to sweat the rotation of the Earth. We'll treat the Earth as if it was not accelerating, basically, for our calculations. Okay, in the future. It turns out there's one more part of this problem that I actually forgot to mention, and that is they ask, hey, what would happen if the person moved to the North Pole or the South Pole? How would that affect this? And so you say to yourself, now, wait a minute. I know that when they're standing on the equator here, they're going around in a circle, right? You say, but what if we moved on to the North or South Pole? We'd be standing at the axis that we're rotating around, yeah? You know what I mean? So now, am I going in a circle? You say, what's the radius of the circle I'm going in then? Well, it would be 0, yeah? If I'm looking top down here, as I head into the center here, right? The circle would be getting smaller and smaller and smaller. When at that point, I'm not going in a circle, just be standing still, like kind of the Earth is rotating under me sort of thing. You're like, I wouldn't really be going in a circle anymore. So if I were standing at the North Pole there, or the South Pole, it's going to be a little easier to draw at the South Pole here, so I'll just draw it there. Right? I'm still going to have a gravitational force pulling me down toward the center of the Earth, and a normal force up from the surface. But now I'm not traveling in a circle. Which way is the radial direction anyway? I'm not going in a circle. The Earth's rotating around, but I'm just staying there, right? And so these forces would then just balance out at the pole. So at the pole, the normal force would equal my weight, right? And the force would balance out to 0, and I wouldn't be accelerating at all on this axis. Okay, so at the poles, right, the total force in the radial axis is 0, right? And so my the forces here would just balance. N would equal mg, right? A bathroom scale, if I was standing on one, it would reveal actually how hard the earth is pulling down on me. It would perfectly balance out. It would push up on me, and the springs in the balance and the lab balance or whatever I'm standing on, the scale I'm balancing on would show a force equal actually to the true force of gravity pulling on me. Okay, those would balance. Here, that gravitational force in is actually going to be a little bit bigger than how hard the scale pushes back up on me. So the normal force, what the scale reads, right, is also what we call our apparent weight. How heavy we feel like we are is how hard that support force is pushing up to support our weight. You see, it's not balancing out the weight. It's a little bit smaller. So, but if I'm at the pole, it perfectly balances out. mg is not significantly changing here. So actually, if you want to, lose weight, at least what the scale reads, if you head towards the equator, that normal force will get smaller, so that it's a little less than gravity. At the poles, that's where staying on a bathroom scale, you would weigh, it would read the most. Anyway, side note. So at the poles, the total force in the radial is 0. Okay, and because we're not accelerating inward toward the center at all, because we're not going in a circle this way, right? So centrifugal acceleration is 0 with that too. All right, that's the last little bit I need to add.